Welcome to the wrap-up video for Chapter 20. This will be our last wrap-up video because the last two topics we have to cover are going to be pretty short, and I don't anticipate that we will need additional work on those. This has been the longest chapter this semester, Chapter 20 on redox. There's much more to redox than balancing redox equations, but we're going to practice more of that in the 4 problems that we're going to do that I did not get to in class, even though it's taken me almost 3.5 lectures to do the other 15. But we're going to do these 4, and these are all good practice problems. So let's go ahead and get started. Number 8 from the PowerPoint and your notes, number 40 from the book, gives us an opportunity to practice redox equations again, but it also enables us to work with our standard reduction potentials. So one of the things that we talked about in class when we first started looking at that page of reduction potentials was that a couple of things. One, if I look at what I have here, let me get my pen working, I see 3 different half reactions, all written as reductions, of course, because that's the way we do it. And I see that the highest one here with the 0.49 volts is my substance that wants to be reduced more than the other 2. The one that wants to be reduced the least is the smallest one, and that would be this one. What this problem is asking us to do is to write the equation for combining 2 half reactions, so an oxidation and a reduction, that leads to the largest positive EMF. Positive EMF, positive E cell, which is E stands for EMF, is spontaneous. We're going to do another practice problem where we're going to calculate E's, convert them to delta G's, because E represents work, delta G represents the energy available to do work, and then we're going to calculate equilibrium constant, so we're going to practice that again. Anyway, you'll see that we'll make some connections between those one more time. So in order for a 2 half reactions to come together and actually do work, the E cell needs to be positive. All right, so we're going to be looking at the 2 half reactions that when I combine them, I get the largest positive EMF, and then we're going to combine 2 where I get the smallest positive. I think that we talked about it briefly in class that it's obvious that the farther apart on the standard reduction potential table and the farthest apart in value, which would be the 2 that I've marked, the lowest and the highest, will give me the largest EMF. So we're going to begin by combining those 2. Now, of the 2 that I've made marks by, which one is going to stay as a reduction? It's going to be this one, the one with the largest reduction potential. So I am going to write my reduction half reaction as is. Now, as I said in class, one of the nice things about the reduction potential table is if you're having some difficulties still with coming up with those half reactions, they're there. So that's kind of helpful. Okay, so here's our reduction, and the reason why it's the reduction is because it has the highest reduction potential. So that is equal to a positive 0.49. The other substance, the one with the lower reduction potential, will be oxidized. So we're going to flip that half reaction, and it'll be gold, plus 4 bromines to give AuBr minus plus 3 electrons. Okay, and the oxidation potential is the changing the sign. So when I combine these 2 that are the farthest apart of these 3, I'm going to get the largest E cell. Now before I can certainly go ahead and add that up, because what I'm about to do with the half reactions is not going to affect the value of the EMFs. I am going to go ahead and my half reactions are balanced, and they are balanced on the reduction potential table, but they're not balanced with respect to one another. I need to multiply this one times 3 so that my numbers of electrons in the 2 half reactions are equal. All right, so I'm going to do that in addition to calculating my large positive EMF. So it's going to come down with 3 IO minuses. Let me stop here and cancel out the things that will cancel. Of course, my electrons will go away. Nothing else cancels. I have only water in the and hydroxide in the top one, so that is not present in the second one. All right, so moving on, 3 waters and 2 golds and 8 Br minuses, bromide ion, 3 iodide ions, 2 gold bromide complexes, and 6 OH minuses. So that's my overall equation. Things we learned from balancing redox equations. My E cell is these two half reaction EMFs added together, and that comes out to 1.35 volts. Positive 1.35 volts. So it's a spontaneous because I have combined something that wants to be reduced and then which has a positive. Now it could be, we could actually have 2 negatives. It's possible. The one that gets reduced does not have to be positive. It just has to be larger than the other one. You may not come out with a combination that gives you a spontaneous combination, but anyway. Moving on to B, where we're going to combine 2 half reactions that gives me the smallest positive EMF. Okay, so the 2 that are the closest together would give me the smaller EMF total. So I'm going to stay with that reduction, so I don't have to change anything in terms of my reduction half reaction. So I'm going to rewrite that. I'm rewriting it without the multiplying because I have a new situation here. Okay, now the E reduction is still, of course, positive 0.49. My oxidation is going to be this one. Okay, and I'm going to flip that reaction because it's going to be an oxidation instead of a reduction. So I think that's, I'm not even sure what element that is. EU. I'd have to look that up. Where's my periodic table? It's an unusual one. Let's see, where is it? I'm looking down at the bottom, but I'm not seeing it. It's really bothering me. Oh well, moving on. EU goes to, so this is an oxidation. Looks like the symbol for a euro, plus electron. All right, so flipping that reaction, and now the E is an oxidation, and I am changing the sign. Okay, so there we go. All right, now in order to add these 2 half reactions, the number of electrons have to be the same, so all I have to do is multiply this one times 2. So coming down here, I have IO minus plus water, nothing's canceling but the electrons, plus EU plus 2 to make I minus plus EU plus 3 plus 2 OH minus. Oop, that should have been 2 EUs. 2. Okay, plus 2 OH minus. And the E cell, by combining those 2 half reaction EMFs, comes out to 0.92 volts. All right, so once we start using the standard reduction potential tables, doing those redox reactions becomes a little bit easier. All right, moving on. Number 11, we are going to write some reactions based on what we're given. The standard reduction potentials are going to become very helpful here. We're going to write balanced equations. We're going to calculate the EMFs. We're going to get the delta G and the equilibrium constant. So we're going to pretty much do the whole thing. The only thing we're not doing here is using the Nernst equation, which we're going to do, I think, in the next problem. All right, so in A, we are going to use this information. Aqueous iodide ion is oxidized to I2. All right, so there's our part of our overall equation by mercury. This is actually the mercury +1 ion. It's kind of a strange one. It's actually a little a polyatomic ion. And then that's all they give us. All right. So what you're going to do is use your standard reduction potential table to help you with the other part of this. What does mercury become? All right, so look up mercury with that species, Hg2 with a 2 plus, find it on your thing. Now, of course, you know iodine is being oxidized and Hg2 plus is being reduced. So you can find it as a reduction on the potential table, and you are going to make Hg2Hg liquid. Okay? So now we're going to write our half reactions, do the whole, the bit to get our balanced chemical equation. Then we'll do our EMFs off to the side as we do that. So oxidation was the iodine. First thing you do when you're balancing a redox half reaction is to balance the thing that's changing. Since iodine is going from a -1 to 0 and I have 2 of them here, I have to put a 2 in front. This is an oxidation. I'm going from -1 to 0. That's a change of 1, but I have 2 iodines, so the number of electrons is going to be 2. Looking up the EMF for this oxidation, I will look for the iodine. Of course, it will be written as a reduction, so I will change the sign of that reduction, and that becomes negative. The E-ox is negative 0.536. So the problem told us that iodine was being oxidized. So we wrote it as an oxidation, given the information in the problem. Looking up the half reaction on the standard reduction potential table, of course, all of those are written as reductions. So this is the reverse of what's written there. So I'm changing the sign of the reduction potential that's there. All right. Okay, reduction. Now you could just copy the reduction potential half reaction that's there, but I'm going to walk you through it as if it weren't there. All right, so we've got 2 mercuries going to, make myself some room, 2 mercuries. The change is +1 per mercury to 0, but I have 2, so it's just a 2 electron change. All right, that'll become important when I start calculating delta G's and K's. How many electrons are involved in the total redox reaction. All right, so looking at the reduction potential table, I don't have to change anything here since this is my reduction, and that is positive 0.789. All right, the electrons are the same in the 2 half reactions, so I can go ahead and add everything together. This is a pretty simple one to start with. The next 2 for the same problem involve an acid, where I'm going to have to add H pluses, and the last one involves base. So we'll get practice with that. Iodine plus 2 Hg liquid, and all I have to do is add up those 2 E's, and I come out with 0, E for the cell, is equal to positive, so this is a spontaneous combination, 0.253 volts. All right, so now we're going to calculate delta G and K for this reaction. And if E is positive, then delta G must be negative. So that is why there is this negative sign in the equation that relates the EMF and the delta G, or free energy. So spontaneous cells, or voltaic cells, that's what a voltaic cell is, a spontaneous combination, are positive. Delta G's have to be negative for spontaneity, so that's why that negative sign is there. Now, in the next 2 reactions, it's going to be important to finish balancing. This one was pretty easy. The number of electrons didn't have to be changed. That's not true in the next 2. So I am going to be using an N of 2 for this reaction. It's a 2 electron change. F is Faraday's constant, 96,485 coulombs per mole of electrons. All right, so we are going to show you how volts turns into joules for delta G. All right, so delta G for this reaction is equal to minus 2 times 96,000 minus 2 moles of electrons times 96,485 coulombs per mole of electrons times 0.253 joules per coulomb. That's what a volt is. The coulombs cancel, the moles of electrons cancel, and I end up with joules. When I multiply these, I end up with a delta G for this reaction of negative 4.88 times 10 to the 4th joules. Now I could go ahead and change that into kilojoules and it would be negative 48.8, but when I plug it into the next equation to get my K, I need to leave it in joules. So I'm going to leave it in joules. My equation for equating delta G's, so here we are with a negative delta G. It's very large. 48, even putting it in kilojoules, is pretty large, but it's a negative. It's a spontaneous reaction. Now we're going to look at the size of K. If it's a spontaneous reaction, and not a equilibrium, probably, I should have a rather large K. And in the case of one of these, the K is, you can't even calculate it on a basic scientific calculator. But anyway, back to this one. So delta G is equal to minus RT ln K. And the reason this minus sign is here is because if delta G is negative, we don't have negative K's, so I have to change the sign. I guess if delta G were positive, you'd end up with taking the ln of a negative number, I don't know, and then you'd end up with a small k. All right, so anyway, so in order to calculate k, I'm going to rearrange this equation. So ln of k is equal to delta G over negative RT. Well, the negatives are going to cancel because I got a negative here and a negative here. So I've got 4.88 times 10 to the 4th joules divided by, put this in parentheses, 8.314, and then this problem said 298, times 298, okay? So when I get that, still ln of k, let me extend my page, so ln of k is equal to, for this problem, 19.7. So all of this right here came out to 19.7. Now I'm going to do that E. I'm going to take the E of the natural anti-log of the natural log. So I'm doing this. So then that becomes K equals, you do that on your calculator, K is 3.6 times 10 to the 8th. So a spontaneous voltaic cell, that's oxymoron, and a spontaneous delta G gives me a rather large K, which I would expect because this reaction is not an equilibrium type reaction. So that's what you would expect. All right. I'm going to go ahead and I think what I want to do is just give us a new page, okay? And that way we can, no, I don't want that. I want a new page. There we go. It's because I want some room for this next one. So if I'm reading from my notes, and you should have that in front of you, or just go back to the previous page. B, in acidic solution. This is B. 11B. In acidic solution, copper 1, with a Roman numeral 1, we know that's what that means, is oxidized to copper 2. So that's a product by the nitrate ion. So copper is being oxidized. That makes nitrate the oxidizing agent. That means nitrate is reduced. So in order to get the product of that reduction, look at your standard reduction tables. Find nitrate, okay? And that half reaction, you can at least get the product. And it's NO. And this is under acidic. So we're going to be using H plus for charge. I'm going to go ahead and not copy the half reactions as on the standard reduction potential table so we can practice this oxidation redox thing a little bit more. So my oxidation is copper 1 to copper 2. Now that will be the opposite of what that will be the reverse of the reaction involving these two species on the table. So to get my, let me finish. balancing the half reaction first. +1 to +2, and this is an oxidation, so electrons always go on the right. So that's a 1 electron change. I look up the E-ox for this, and it'll be the opposite of what I find when I find this change on the standard reduction potential table. So I look at that, and it is negative 0.153 because it is the reverse of this written as a reduction. All right? The thing that is a reduction is exactly like it is on the page, but I'm going to go through it as if it weren't there in terms of the half reaction. We are going from a +5 for nitrogen to a +2. Okay? That is a 3 electron change. We are in acidic conditions. I've got 4 negatives on this side. I have no charge on this side. So I'm going to add 4 H pluses. All right? And then for my oxygens, I've got 3 on this side, 1 on this side, so I need 2 waters, and that balances everything out. And this is exactly what you see on the standard reduction potential table in terms of this half reaction. The E for this reduction on the table is positive 0.96. All right, so now I've got to do some multiplying, just something simple here, times 3. Now I will not be multiplying this oxidation potential by 3. We haven't done that before. We're not going to do it now. That does not affect this. That 3 is there to balance this particular combination, but it does not affect the EMF for that change. All right, so taking and bringing everything down, the only thing that's changing here are the canceled out are the electrons. Plus 4H plus makes 3 copper plus 2s plus NO plus 2 waters, and adding my 2 E's, I end up with an E cell of 0.807 volts, and that's positive. So it's a spontaneous combination. Now we will calculate our delta G from this EMF. Okay. Times my E. Okay. So it's a 3 electron change. So minus 3 times 96,485 coulombs per mole of electrons times the 0.807. When I multiply those 3 things together, I end up with a delta G of negative 2.34 times 10 to the 5th joules. Okay. Now we will take that delta G and we will calculate our K, because we're going to take delta G over negative RT equals ln of K, like we did previously. The negatives will go away, and ln of K is equal to 2.34 times 10 to the 5th joules over, I should just go ahead and multiply these 2 things in the denominator since they're used every time. But when I do that, my ln of K is equal to 94.3. I take E to the ln K equals E, ln K up here, equals E to the 94.3. Plug that in on the calculator, and K is equal to 9 times 10 to the 40th. Now I'll tell you that the solutions manual did not do this step right here correctly. They got something different. And I double checked it. So very large K, negative delta G, positive E, all goes together to say that this reaction happens as written, spontaneous, not really an equilibrium reaction with that large of a K. Okay? All right, we've got one more, C. Okay, C. Reading from the notes. In basic solution, CrOH3 solid is oxidized to the chromate ion. okay, by hypochlorite, an active ingredient in bleach. I'm going to consult my standard reduction potential table to make sure that I know what the product is for this. It is the chloride ion. Okay, so then I'm going to split this up into the two half reactions, look up my E cells. Of course, it'll be opposite for the chromium, so let me go ahead and do the oxidation first. Okay, let's go ahead and just balance. Now, this is in basic solution, so I'm going to be using OH minus for balancing. Excuse me. I am going from -1 on hydroxide. I've got 3 of them. That makes chromium +3 to +6 here. -2, -8, they have to add up to -8, has to add up to -2. So this is a 3 electron change. I got 1 chromium on each side. This is an oxidation. Those 3 electrons go over here. All right. Base. I have -5 on this side for charge. I have no charge on this side. So I need to add 5 OH minuses over here, okay, to make the charge the same. Now look at your oxygens. 3 plus 5 is 8. I already have 4, so I need 4 waters to balance the oxygens. 8 hydrogens, 5 and 3 is 8. So my half reaction is balanced. Could have copied it off the table, but I wanted to practice. And when I look this up on the table, I see that the oxidation is going to be the opposite of what is there because I've flipped the reaction around, and it's a positive 0.13. All right, my reduction, already have that. Let me do some erasing. Okay, my reduction is the hypochlorite ion going to Cl minus. That is a change from +1 to -1, so that's a change of 2 electrons. Okay. Charge, I've got a -3 on this side, -1 on this side, so I need 2 hydroxides. That gives me 2 oxygens here. I have 1 over here, so 1 water will do it. 2 hydrogens, 2 hydrogens. Okay. So now my half reaction is balanced, and I look up the reduction potential straight off the table, and it is equal to positive 0.89. Okay, so now I need to look at those electrons and those 2 half reactions, and they're not the same. I've got to multiply this top one by 2, the oxidation, and the reduction by 3. Again, that is not going to change my E cell. I'll go ahead and even do that. E cell is equal to 1.02 volts. All right. This all added together with the multipliers, what cancels? Electrons cancel. Some of the waters cancel. This was 8 waters after the multiplying. This is 3, so those waters are gone. This becomes 5. 10 hydroxides versus 6, so that becomes 4 hydroxides, and these are gone. All right, so this is what I end up with, 2CrOH3, and if you need to do it 2 steps, go ahead, but I'm not. 4 hydroxides, 3 hypochlorites makes 2 chromate ions, 3 chloride ions, and 5 waters. All right, so there's my balance. Now, the first thing we're going to do is calculate our delta G. And you almost have to do the 2 half reactions in order to see that N is 6. This is a 6 electron change times Faraday's constant times our EMF. Okay, multiplying those 3, we end up with a negative 5.90 times 10 to the 5th joules. Getting our K from that, delta G over negative RT, the negatives go away, so that was a negative, 5.90 times 10 to the 5th divided by that 8.314 times 298. Now that comes out to 238, and that is equal to ln K. I'm not finished. So E to the ln K equals E to the 238, and I don't know about your calculator, but my calculator gave me an overflow error on this. It's such a large number, so I did consult the solutions manual, and they also said large, but they had the number. So K is equal to 3.3, maybe your calculator can do this, times 10 to the 103rd power. Amazingly large number. From a negative delta G, positive E, definitely not an equilibrium reaction. So this problem here was a long one. The reason why I skipped it in class, but it is an excellent wrap up to a lot of what we've talked about in this chapter. All right, moving on. All right, here we're going to be using the Nernst equation. We did one or two of those in class, but didn't have enough time to do more. So here, let's do it one more time. All right, so the Nernst equation is, turn to that page, my notes, is we use it when we are trying to calculate the EMF for a cell when we're not under standard conditions. And we had a corresponding type of an equation for delta G's when we're not at standard conditions and so on. So here's the equation. Over N, which is your electron change, times the log of Q. All right. So we're going to have different concentrations. This could be used for a concentration cell where you've got the same stuff on both sides, but it's different concentrations, and you therefore get some current to flow. All right, so let's identify what we have. Here's our reaction. 10 with a +2 aqueous. We've got a couple of solids, so when we do our Q, remember we won't be putting those solids in there. So in fact, the Q is going to be, let's just write down what that is. It's Pb +2, the concentration of the product, over the reactant. So this is all that Q is, because the two solids that are present. So it says, if the concentration of 10 in the cathode half cell is 1 molar, so we'll be putting 1 molar at the bottom, and the cell generates a current of 0.22, so this is right here. What is the concentration of lead in the anode half cell? So I'm solving for the Pb concentration. What I don't have is E under standard conditions, but I've got a reaction, so I can calculate it. So the first thing we have to do is get our E under standard conditions, and that is 10 is being reduced, so I'm going to find the reduction potential for 10 and leave it alone. Okay, so E for the reduction is equal to, look for 10 on your standard reduction potential, going from +2 to 0, and it is -0.136. The oxidation is lead going to lead 2, so find that, and then you're going to flip the sign, so it's a +0.126. All right, so the E for this cell is equal to -0.01. So it's negative. It's not a spontaneous combination. That's okay. We're going to plug it in anyway. The E that we're given for this different, when we're not under standard conditions, is positive. So 0.22 is equal to a negative 0.01 minus 0.0591. What is our N here? 2 electrons for this, 2 electrons for that, so it's 2 times the log of Pb plus 2, essentially over 1. All right? So collecting terms, I have to bring the 0.01 to the other side by adding it to both sides, so that becomes 0.23 equals negative 0.0591 over 2 log of Pb plus 2. Really? Okay, because it's over 1. Dividing this out and bringing it, dividing both sides by it, I end up with a negative 7.77 equals log of Pb plus. Okay. Then I do the anti-log of both sides. So I'm going to double check my numbers here, but I'm pretty sure I'm correct. So let me just do a little quick calculation. Okay. So I've left out a step here to go from here to here. This term right here, okay, comes out to 0.0296. So negative 0.0296. I'm going to divide both sides by that, okay? So I'm going to do it over here. 0.23 divided by negative 0.0296, and that is equal to the log of the Pb, all right? So do I indeed get the 7.77? Just double checking. Yes, I do. So now I'm going to take 10. I'm going to do the log of both sides. So to get Pb plus 2, I am taking the anti-log of both sides. So when I do 10 to the log of this, that is equal to 10 to the minus 7.77. All right, so Pb is equal to the anti-log of negative 7.77, and lead is equal to 1.7 times 10 to the minus 8 molar. 1.7 times 10 to the minus 8 molar. Okay, that's it. B. If the anode half cell contains sulfate in a concentration of 1 molar in equilibrium with some solid lead sulfate, what is the KSP? All right, so you are going to write your equation, and I know this is what students have the most trouble with. We're talking about KSP, so the equation I need to write is this one. And they want to know the KSP, so you have to know the concentration of both of these. Well, I do. I just figured out the concentration of lead, and they told me the concentration of sulfate. I'm going to plug those into the KSP expression, and it is just, it's 1 to 1, so there are no exponents. Okay. So KSP is equal to essentially 1.7 times 10 to the minus 8. Because I'm multiplying 1.7 times 10 to the minus 8 times 1. So 1.7 times 10 to the minus 8. Okay. Little chapter 17 review as well. All right, one more problem and we're done with this wrap-up video. All right. Based on standard reduction potentials, would you expect copper metal to oxidize under standard conditions in the presence of oxygen and hydrogen ions? And then they're talking about Statue of Liberty being refurbished, which has a copper skin, which is why it's green. It's got a green copper oxide coating, but of course the skeleton is made out of iron. So they want to know, why are you putting spacers between copper and iron? All right, so would you expect copper metal to oxidize? So if I looked at the standard reduction potentials, and I looked at the oxidation of copper to copper plus 2. Now you're asking, how do you know which one it is? Well, I'm telling you that the plus 2 charge for copper is more common than the plus 1. Anyway, as an oxidation, that E is, as an oxidation, I've changed the sign of what's on the table, negative 0.337 volts. All right. Oxygen, in the presence of hydrogen ions, all right, the reduction in it being reduced to, look at your table of reduction potentials, find oxygen, O2, it would have to be reduced if copper is being oxidized. So find oxygen. Oxygen in the presence of hydrogen ions gets reduced to water. All right. The reduction potential for that reaction is positive 1.23. Did I look at the right one? All right, I'm looking. Yes. 1.23 volts. All right. Don't get confused by, let's see, there's oxygen going to peroxide. We're not doing that. We're not using ozone, O3, and we're not basic, so we're using the 1.23 reduction potential for oxygen. Anyway, if copper, would you expect copper to oxidize under standard conditions? Well, if I combine these two, I get a positive EMF, and we know that copper oxidizes because that's why the Statue of Liberty is green. So the answer to this question is yes, and the reason why is because I end up with an E cell that's positive, and if I do the math, I end up with an E cell of 0.89 volts. So yes, we would expect it to happen. Copper oxidizes in the presence of oxygen and hydrogen ions all the time. So when the Statue of Liberty was refurbished, Teflon spacers were added to separate the iron from the copper. Why did they do that? Well, let's look at standard reduction potentials. If I take the iron skeleton and I oxidize it, the oxidation is 0.440. Let me back up, because I left something out in my notes. All right, so let's look at iron versus copper. In 131 or 100, high school, wherever you've thought about the activity series before, iron is above copper, all right, on the activity series. That means iron gets oxidized and copper gets reduced. Well, you might think, well, if copper were reduced, we wouldn't have a green coating. It'd be nice and pretty in copper. But then iron would be oxidized, and you'd be essentially taking the iron skeleton and it would be falling apart. Because iron would no longer be iron metal, it would be iron plus 2, which is rust, and it wouldn't be really good for the Statue of Liberty. So if we look at reduction potentials as a way of explaining this, because we're sophisticated now, the reduction potential to take reduction potential to take iron from plus 2 to 0, or I don't know where the plus 3 one is. It's not here. So the plus 2, let me write the reduction potential I'm talking about. So here's the reduction potential for iron. And it is a negative 0.440. The reduction potential for copper, which you will find on your standard reduction potential table, find copper, is, just had it up here, it is positive 0.337. So according to the reduction potentials, just like the activity series, iron will not be reduced, iron will be oxidized. And it'll be a positive 0.440, okay, and copper will be reduced. And like I said, that might be pretty good for the outside, but it wouldn't be good for the inside that holds the whole thing together. So the Teflon spacers are there to keep the reaction from happening, which would be iron would be oxidized, copper would be reduced, and the Statue of Liberty would no longer be standing. So that's what role the Teflon spacers play. They are keeping two metals that would be a spontaneous reaction because I'd be taking this negative 0.440, I'd be making it positive because iron would be oxidized. The two added together come up with a positive EMF, spontaneous reaction. Goodbye, Statue of Liberty. All right, that wraps up our wrap-up video for chapter 20. Long chapter, a lot of stuff here, important class of reactions. Thanks for your attention.